Good afternoon, everyone. Welcome to the afternoon session on the last day of the technical conference. This session is on probabilistic circuit models. And I would like to invite the first paper, or the speaker for the first paper. The first paper is on local message passing on frustrated systems. The authors are Luca, Schmid, Joshua Brenk, and Laurent Schmalen. And let me invite the speaker. Welcome.
So thanks for the kind introduction. I'm Luca from Karlsruhe in Germany, and I want to present this work on local message passing for frustrated systems. So let's get on track. We are dealing with probabilistic inference. So we are considering a system as a set of random variables, and we want to basically infer the state of the system given some possibly noisy observation. And yeah, using Bayes' theorem, we can also incorporate prior knowledge here. Now, especially we are interested in marginal inference, which means that we want to infer the state of one single variable. And to do so, we basically need to marginalize out here all these other variables. And this basically can become quite computationally complex if we deal with a great or large system. So what we usually need to do is to come up with some kind of efficient way to do so. And I want to motivate here to use message passing on graphs to do so. And for this, we assume that our system has a certain structure, so that the variables are somehow independent. And this translates into this factorization in the probability density function. Now, let's have a look at a short example. Here we have a system which has 3 variables and this factorization here, and we can illustrate this system with a so-called factor graph, which means that these variable nodes here, the circular nodes, they correspond to the variables, and the factors are represented by these squared nodes here. And each squared node, it's called a factor node, is then connected to the variables on which it depends. Now, how can we do this marginalization more efficiently? Basically, if you have a look at this formula where we want to marginalize towards x1, then we can simply rearrange these terms, so using the distributive law, and come up with a more simple computation here. To visualize this on the graph, this would mean that we at first remove all the nodes which directly depend on x3, and we can compress them as sort of as a message, which now flows within this graph. And now if we do the second sum over x2, we can basically reuse this message. So we don't need to consider this part of the graph anymore, but we can just basically divide and conquer, and this is what message passing is all about. We can formalize this idea into the well-known sum product algorithm, also known as belief propagation. So yeah, as we saw, this is a message passing algorithm, and it's basically only defined by this one relatively simple update rule, which defines how we basically update these messages on the edges of our graph. So I won't go into detail, but to basically compute a message, for instance, this green message going towards x2, we just collect all the incoming message to this factor node here. In this case, we only have one incoming message. And it's important that we don't consider this message which flows here in the opposite direction. This is very important. It's called the extrinsic principle, and basically avoids double counting, so that we are basically double counting information from the other side of the graph. Now, this sum product algorithm is very commonly used because it's quite simple. We only need this local update rule, which is then applied on the graph, and then we basically propagate messages within this graph and come up with the marginals for all the variables. Another interesting property is that we can also apply this local update rule for cyclic graphs. And this is quite commonly used because many of real-world applications lead to cyclic graphs. But of course, in this case, we have a different situation because firstly, messages can now propagate within these cycles. So we have an iterative algorithm. And secondly, the original idea of the sum product algorithm is now not anymore valid, because if you recall the example from before, if we want to marginalize out x3, here we would draw this box and remove all the nodes within this box. But now we have basically, due to the cycle, 2 outgoing edges, which means we cannot represent this local marginal within one message which is flowing on one edge of the graph. So to summarize, we can still apply the sum product algorithm on cyclic graphs, but we only will use an approximation. And especially the algorithm will be iteratively here. To be more precise, we can use a very nice connection which made Yedidia in a former work. And he found that the fixed points of this sum product algorithm, so of this iterative message passing, that they correspond to the stationary points of the so-called Bethe free energy, which is a result from statistical physics. And we will need this Bethe free energy later, but for here it's just interesting to see the different types of errors which we can make by applying the SPA on cyclic graphs. So at first we are not ensured that we will converge when doing message passing. And even if we converge, we might end up in a local minimum of the Bethe free energy and not a global one, which we would originally want to go to. Based on this insight, there were a lot of attempts to come up with better algorithms for marginal inference. One idea would be to simply directly minimize this Bethe free energy term. And there's a very nice algorithm which does this in a concave convex procedure. However, it's more complex than the very simple sum product algorithm. And this is why there were also a lot of attempts which try to use the sum product algorithm on cyclic graphs, but try to somehow improve it or mitigate its suboptimality. For instance, one very common approach is neural belief propagation. Here we are basically unfolding this message passing to basically a neural network. We apply weights on the messages and tune the weights such that the performance will be improved. However, we want to go a different way here. We want to stick with message passing because it's a very natural way to compute marginals on a graph. But we don't want to use the sum product algorithm because we saw that it's basically derived for tree structured graphs. So it's basically a mismatched algorithm here. So we want to come up with a new update rule, which is better suited for cyclic graphs, such as the SPA is very well suited, in fact, optimal for tree structured graphs. So to summarize, we want to find a new message update rule, which is basically a local function or mapping, which defines how to compute an outgoing message based on the incoming message. And this function should only depend on this local factor psi here. Earlier, we saw the extrinsic principle for the SPA, which means that we do not include this message which flows here in the opposite direction. And this was motivated to avoid double counting in the graph. However, if we deal now with cyclic graphs, we cannot avoid double counting because basically messages, if you imagine here a cycle, messages will propagate within the cycle anywhere to their origin back. And this is why we also investigated a second mapping, which is basically non-extrinsic, so which includes this red message here in its mapping. Now, based on these two architectures, we now want to learn this mapping actually. And to do so, we just used a very small neural network, only one hidden layer with 7 neurons, because basically these mappings are quite simple. And the idea is now to apply message passing in the graph. And at every node, we apply this very simple mapping and tune this neural network at the end, basically in an end-to-end procedure towards a good marginal inference performance. And so we are basically finding or hope to find a good mapping, which is better suited for cyclic graphs. To do so, we also need some loss functions for this inference performance. One way would be to go with the KL divergence between the beliefs. So these B terms are basically the result of the message passing, and they should well approximate the true beliefs. But of course, the true beliefs are not always available. This is the whole reason why we are doing this. So a second approach would be unsupervised. And here we are coming back to this Bethe free energy term and simply propose to minimize towards this Bethe free energy. I showed here the formula of the Bethe free energy just to show you that it does not depend on the true marginals, and it basically only depends on these beliefs, so the result of the message passing, and these psi factors, which are the local factors here of the graph, so this is basically a very local loss function. And additionally, we also apply some regularization here. We call it the Bethe consistency distance. And this is basically should ensure local consistency of the beliefs, which means that if we take such a pairwise belief, so it still depends on two variables and marginalize out one of these two variables, then this distribution should be close to the single beliefs which we get. Now, having set up these loss functions, we are ready to have a look at some example. So here we are considering the Ising model, which comes from physics, and you can imagine basically each of these variables to be a magnetic spin, and it can basically have a positive or negative magnetization. And we have local fields which are directly applied to only one spin, and then we have local couplings between each of these variables. And a negative coupling would mean that these spins are interacting repellively, and a positive spin means that they are attracted to each other. Now, actually coming back to the title of this presentation, what is a frustrated system here? In this example, this would mean if we choose all the couplings to be negative, then we get up a frustrated system, because basically if x1 wants to be different to x2 and x3, but at the same time these two variables also want to be in a different state, we cannot fulfill all these local requirements, and this is basically called a frustrated system. Now, to sample actual graphs from this model, we can use spin classes, which simply means that we are randomly sampling these local fields and these couplings within each graph from a uniform distribution. And thereby we basically get data on which we can now train and evaluate. So these results are averaged over 10 to the power 5 graphs here. These are basically our baseline. So the sum product algorithm, of course. And the second term was the direct minimization of the Bethe free energy in this double loop algorithm. And on the right-hand side, I visualized the mapping which we see from the sum product algorithm. So again, for instance, looking at the negative coupling here, we are looking at this blue line, and we see that for a positive incoming message, we would become a negative outgoing message, which corresponds to this repellive coupling here. Now let's have a look at what we found actually. So this is the new mapping which we found in the extrinsic case. And here in this column, you also see basically the approximation quality, and we already improved quite a bit from the original sum product algorithm. And even more surprising was that the non-extrinsic update rule even outperformed this. So basically, this was actually true that for very cyclic graphs, in this case, a fully connected graph, these extrinsic rules doesn't hold anymore. Lastly, we also have the same results for training in an unsupervised manner. And here we can see the performance diminishes a little bit. Interestingly, for the extrinsic case, we had even a better performance. And this is basically because we used gradient descent to optimize. And it seems that this regularized Bethe free energy, which we used, is somehow better suited for this optimization than the KL divergence. Okay, now let's have a look. We take now these mappings which we found and apply them to other types of graphs to just see if they generalize. So now we are considering graphs with constant parameters. And this means that each cell in this graph here basically represents the evaluation on one graph, which has a constant local field at every variable, and also a constant coupling at every coupling within this graph. And the color indicates basically the KL divergence to the true marginal, so basically the approximation quality. And we see for the sum product algorithm that especially here for negative couplings, so for these frustrated systems I mentioned earlier, there's a very bad behavior here. And in comparison, the CCCP algorithm, so this direct minimization, performs quite better here. Now, this is our mapping, which we found in the extrinsic mapping. We see that these regions of bad approximation are somehow reduced. And the best result was given again by this non-extrinsic mapping, which has basically a good approximation quality over the whole space which we considered here. So this is already it. To conclude, we found an alternative, or we searched for alternative message update rules, which are basically better suited for cyclic graphs than the sum product algorithm is. And we made a first approach here using a small neural network. Especially, I want to emphasize this extrinsic principle, which is not anymore true if we have a lot of cycles in the graph. And secondly, this regularized Bethe free energy term, which we proposed as an unsupervised way to train such models for marginal inference. And this is basically not restricted to our problem here, but this is basically a general loss function which you can apply for marginal inference in many cases. Also, basically some kind of advertisement for the poster session afterwards. I'm originally coming from communications engineering, and so we originally developed this algorithm for a specific problem in communications engineering, which is basically symbol detection. So inferring symbols, which are basically, for instance, bits or other symbols, which modulate an electromagnetic wave, and inferring them back at a receiver. So basically what your phone does every day if it receives some information. If you're interested in this application, just come to my poster. I left this part out because it would need a lot of introduction for terms which you probably are not so familiar with. But yeah, just come to my poster. Yeah, we are still working on this task here. We are investigating it. At first, we were investigating the larger graphs and also different topologies. So not only fully connected graphs, and also an idea which actually also came up during the discussions with the reviewers is that we can, for instance, increase this neural network that we use and incorporate more knowledge, for instance, the degree of the graph at a specific time, or even learn different mappings for different number of iterations. So this is very interesting. Or going into the opposite direction would be, we saw that this mapping that we found was very simple, so we could also just use a very simple parametric function to learn this instead of the neural network, so even further reducing the complexity here. And this brings me already to the end of the talk. So thanks for your attention.
Okay, so the discussant is here, I guess. It's Kijung Yoon.
Thank you for the nice presentation. I'm Kijung Yoon from Hanyang University, Seoul, Korea. All right, so let's dive into some main takeaways from this study. First off, the authors focused on the understanding the behavior of different approximate inference models, and they ran some cool numerical experiments on tiny 2x2 Ising models and used vector graphs for symbol detection. Next, they looked at the impact of three important factors. First, non-extrinsic update rule. So this means that they leveraged both extrinsic and intrinsic messages at the time of updating factor to variable messages. And you know, in a generic tree-structured a cyclic graph, we don't usually double count the opposite direction of the factor to variable messages, which is the intrinsic message. But they decided to incorporate it when dealing with the cyclic graph. So of course, this is the kind of strategy that we hope to see realized within the framework of model-based approaches, which will be discussed right next. Second, model-based approach. So they tried using a neural network-based message function as opposed to the conventional way of algorithmic inference. So, however, I would like to emphasize that this approach has already gained a lot of interest, and there are many previous works on developing the neural inference models. So third, unsupervised training. So here they proposed minimizing the Bethe free energy combined with the regularization term defined by the Bethe consistency distance during training, which is interesting. So all these strategies actually improve the predictive performance, which is pretty awesome. But there's a tiny catch. So the unsupervised training seems to have a little bit negative effect when combined with the previous two approaches. Okay, interesting. So now this is all about the takeaways that I thought about. So now let's talk about some open problems that they want to explore. So I have three main questions. So first, I wonder what happens when the graph size changes. So more specifically, what if we test the model on like 10 by 10 grid graph instead of 2 by 2? So which is going to be the simple extension, right? So yeah, that's something worth digging into. So second, I also want to see how different graph structures affect the model's generalization ability. You know, there are tons of graph topologies, and there are many established random graph generators they can use. So it's important to know how the model handles this kind of variety. So lastly, I'm curious about how the models deal with different input distribution. So when I say input distribution, that means kind of Ising model parameters like coupling strength J and feed-forward local evidence theta. So it'll be cool to see how the models handle different ranges of these input values. So by tackling these open problems, we can really understand the ins and outs of this proposed the approximate inference models and how well they can be generalized to the real world applications. So that's all about my discussion, and thank you for your time.
So thanks a lot for these comments. Yeah, as I mentioned, basically, we are working on this. So we are currently trying out different graph structures. We started with fully connected graphs and just scaled up the number of variables which we used. And there we saw basically that it kind of generalizes, but of course, if you increase the number of variables in a fully connected graphs, then this kind of damping, which we saw at the message update, will increase, of course. So there's basically a trade-off. We can learn one message update which tries to deal with all kinds of structures. Then we will end up in some kind of compromise. Or as I mentioned, the other way would be to adapt to these different environments by incorporating more knowledge in the mapping. But of course, then it will become more complex. So these are the trade-offs which we already see. But yeah, we are still within the evaluation of these different kind of environments. So I cannot tell too much here. Yeah, maybe one. Yeah.
So maybe this is a good time for one or two questions. So no questions. I have a question. So maybe a clarification. I didn't get how many times do you have to train? Namely, if you are only working on Ising models, then you're training on a 2 by 2, and then you are applying it to any size, right? The same, what you learn, you apply to any size Ising network without any change. But what when you have to move to another type benchmarks, would you have to train again and apply? So it's per benchmark type of, is that right?
Yeah, basically we have two options. We can either train on a small model using, for instance, the supervised training, and then hope that it generalizes for larger graphs. This is what we see, but
of the same type.
Of the same type, yeah. Or the other direction would be to train on the actual model that we want to then also use with the unsupervised training, because for large graphs, we cannot use the supervised training. So these are basically two strategies which we want to compare and see what performs better. And right now, the tendency is that basically using this constrained Bethe free energy as a loss function is better suited, and then specifically train for one task. So, yeah.
Okay, thank you. And just one comment. I mean, since you have a general purpose algorithm, you are invited to participate in the competition that we have. I mean, I don't know if you were here, but that's an opportunity. Okay, let's thank the speaker again.